Okay, so today we're going to look at one more type of test for a series. I just talked to my class and they said so far we know about geometric series. We can use that test. We can use the divergence test to test if something diverges, not to confirm that it converges. And we can look at telescopic series, the most brute force approach. This is kind of a much higher order, a much more elegant type of test. It's not one that you always want to rely on. It works for a huge number of different kinds of series, but it takes a long time to complete. We're going to go over it early though. My analogy was it's kind of like the quadratic formula. The quadratic formula takes a long time to do, so you try to avoid it by factoring or using square roots or something nicer and simpler if you can. But this is a nice fallback strategy. So this guy, let's apply the divergence test to it in our head. Does it diverge by the divergence test? No, because its limit is, the limit of the sequence is 0 as you approach infinity. That doesn't mean it doesn't diverge, it just means the test fails, we can't say. So maybe it diverges, let's find out. So the integral test is another test. It's kind of strange that you combine integrals and series, but in higher level math that happens all the time. Lots of problems have derivatives in them, series in them, integrals in them all at the same time. You can use these things, they're all just different tools for doing all kinds of different things. So the test says this though, it's a theorem, right? So if then, if f is continuous and decreasing at least for x greater than 1, so you got to meet all those criteria. It's got to be continuous, it's got to be positive, strictly positive, it's got to be decreasing. And you basically think about that function being the function mapping onto the sequence. This is just technical jargon, not really important, right? This is important, and this is important. You've got to check all three of those before ever applying the integral test. But if those are satisfied, then the series and the integral, improper from 1 to infinity, behave the same way. Either they both diverge or they both converge. And see, we know lots of stuff about integrals, so we'll know what happens then, if that makes sense to you guys, if we meet the criteria. So does this function, this first example, does it satisfy the criteria? Is it continuous? And really it just has to be continuous from 1 to infinity too, right? Sequences, series just go from 1 to infinity. Yeah, it is. What do you mean, Kylie? Aren't you worried it's a fraction? That could be discontinuous. It could have an asymptote, right? It's squared though. The bottom's never 0. So let's say that. Let's say you got to check these and show it. This is continuous since the denominator denom is never 0. So it's continuous for negative infinity to infinity. Okay? Check. Is it strictly positive on 1 to infinity? You have to worry about other places, just 1 to infinity. Well, yeah, the bottom's always positive no matter what. And if you put counting numbers from 1 to infinity and on the top, aren't you going to be positive there? I don't think we need to really say much about this. We can just say, yes, it's positive from 1 to infinity. Now, how do we show it's decreasing? The other day, when we were looking at sequences with monotonic and monotonicity of sequences, we looked at one way to do it. We looked at the current term and like the n plus 1 term, and if we wanted to see if it's decreasing, then the n plus 1 term would have to be smaller then, because the next term would have to be smaller. Okay, you can do this that way as well, but I want to do it a different way just to show you your two tools. Both ways are equally legit. This way is going to review some important stuff. You can also use derivatives to show that things are increasing or decreasing. Isn't that what taking a derivative shows? So I'm going to take the derivative of the function. So I'm going to say, just pretend these are x's. Well, let's just leave them as n's. You can leave it as n. What's f prime of n? What rule am I going to have to use? Quotient rule. So ho d pi minus, you guys are laughing at me, minus phi, oh, almost forgot my d ho,
over ho squared.
Over ho squared. Now that looks ugly. Remember, we're just trying to establish that this derivative is hopefully negative because we want decreasing, right? We want to be decreasing, getting smaller over time. In other words, as we've been talking about with series. So I just need to simplify that guy and see if something happens here. So we've got n squared plus 1 minus 2n squared over n squared plus 1 squared. That combines like terms on top to negative n squared plus 1 over n squared plus 1 squared. So what do you guys think? Is that negative? Is that positive? What's going on? Think about each piece separately. The denominator is squared there and squared there. Doubly positive, if you know what I'm saying. Like, there's no way you can make that negative. On top, it's strictly negative, right? Now you're saying, well, like maybe for some ends it wouldn't be negative, but you guys are saying except for 0, like things 0 and like 0.5. But remember, we don't have to be decreasing everywhere. We just have to be decreasing over where the series is being added up, which is from where? 1 to infinity. So from 1 to infinity, is that guy negative on top? Cool. So this guy is negative over positive equals negative. We're going to say, in other words, f prime of n is less than 0. It's negative, and I'm going to write fancy math here, for all n greater than or equal to 1, which is what we need. So I want to start seeing this kind of fancy math jargon in yours. It's going to get you ready for higher level math, plus it's the easiest way to write it down instead of writing lots of words. Okay? If you want to write it in words, though, that's still okay. Alright, so we can actually use the integral test. Sweet deal. So we need to look at the integral now. Notice, why did I switch from n to x? Because now we're using a continuous type thing, and the connotation is that it's a discrete type thing. 1, 2, 3 type thing. X is like 1, 1.2, 1.75, you know, all that stuff. So can we do this integral?
Yes.
Yep. It's a simple u sub, isn't it? What's it going to be?
X squared. Okay.
1/2. And u is the denominator, so ln of x squared plus 1 plus c, but remember we got an improper integral going on here, so let's write it out the right way. So really I've got to say from like 1 to infinity here, right? So let's say the limit as b approaches infinity of, let's take the 1/2 out, right? We can factor the 1/2 out. So we're going to have natural log of x squared plus 1 evaluated from 1 to b. So that's going to be 1/2. And now if I put b in, then I'm going to have the natural log of b squared plus 1 minus the natural log of 2, which is, I don't need my absolute value bars. 2 is 2 in absolute value. And I've got a limit in front of this guy. I should have stuck it right there, right? The limit as b approaches infinity. So that's 1/2. Ooh, if b approaches infinity here, what's that going to be? I think that's going to be infinity, right? Minus the natural log of 2. So I think that this integral diverges. Yeah? So that's going to be infinity. So that shows that the integral diverges, so you've got to write it like this though. Write your conclusion out. Therefore, or so, or something like that. Therefore, the series also diverges by the integral test. You can do some abbreviation, but you don't want to do too much. The AP exam over the last 2 or 3 years has been merging more and more towards heavier explanations. And if you take this stuff in college, your professors are usually much heavier than the AP exam. They expect you to be very explicit with your explanations. Like, I don't even know if I'd have scored 100% on this question if I did this in my Calc 2 class. My teacher was very picky, and rightfully so. To do higher level math, you got to know how to say it just right, you know what I mean? So saying it just right is part of the understanding. So there's our first example with the integral test. You guys want to try another one? Let's do another one. Same test. We got time. This guy's not due till Monday or Tuesday, probably Tuesday. I just go for Tuesday. We'll see. We'll talk Thursday. Okay, there's another example. It's clearly not. Let's go through our list. It's not geometric, right? Duh. Could it be telescoping? It's so close. If this was minus instead of plus, you could factor it, do partial fractions, and probably create something that's telescoping. In fact, I think you guys had a problem like that in your last section. Yeah? But it's plus, so you can't do partial fractions on it. Divergence test. Limit of the sequence is 0, inconclusive. So we've got to apply the only other thing we know so far. So check marks. Is it positive? Duh. Clearly positive. That's good enough. Okay. Is it continuous? Just like the last one, same kind of reason. There's no asymptotes anywhere, let alone in between 1 and infinity. So let's say it's continuous on negative infinity to infinity, so duh. On 1 to infinity.
If we put that on the AP test.
Oh, I think you'd be fine. It's extra clear. I mean, it makes things super clear. If you were wrong and then you put that on there, yeah, that'd be a problem.
Duh. Why did you get this answer? Duh.
Okay, so f prime. You gotta use the quotient rule again, but this time it's gonna be nicer, right? You guys help me, I'm not helping. Tell me what to write.
1.
0 plus minus.
Because the first part's 0, because the derivative of the top is 0, right?
Yeah.
So bottom derivative of top is 0 minus
2
Ends. 2n. All over. All bottom.
that thing.
Square.
This one's even more clear-cut than the last one, isn't it? The top is clearly always negative for all values of n, unless n is negative, but we're not worried about those. And the bottom is clearly always positive for anything. So this is definitely negative for all n greater than or equal to 1, which is what we're looking for. So decreasing on 1 to infinity, check, check, check. We're going to be checking lots of conditions, so I want you to get used to that. You don't have to put the check mark, of course, but it's good for the thought process. Okay, integral time.
2.
This is a super easy integral. Arctangent. Oh, I should have put x. My bad. Let's get our limit. So the limit as b approaches infinity of inverse tangent of x. 1b. It's going to be the inverse tangent. Oh, get my limit. Inverse tangent of b minus inverse tangent of 1. And let's see if you guys remember what inverse tangent looks like. As you approach infinity on the inverse tangent graph, you go to pi over 2, because here's tangent, pi over 2 each way. Inverse goes like that, right? So this is going to be pi over 2, and there's no b there. The inverse tangent of 1, that was a unit circle calculation, right? 45 is the answer. So pi over 4. So this guy is pi over 4. But that's not really the answer we were looking for. Remember, that came out finite. So this converges. So that converges. That's what you've got to say at the end. Make your conclusion nice and explicit. So I'm going to say, therefore, by the integral test. And you can do some abbreviating type things, like by the integral test, the series converges since the integral from 1 to infinity converges. Okay? I'd advise trying to avoid abbreviations, but if you're, I know some of you can't avoid it, so that's okay. Alright? I'll see you next time. We'll look at one more test, which is a lot easier than this one. This is our last resort test because it takes a long time. We'll look at P-series, which are super easy, next time.